Hello everyone, welcome back. This in this video I provide more information about some of the details that you need to solve part of the problems in chapter 5. Here we are doing the transform analysis of linear time invariant systems. So it's more understanding about the Z-transform itself, some things that we know, and we know, for example, that everything is related to the convolution and so on, how to calculate the output of a system if we are given the impulse response and the input. So now we try to make a connection with the Z-transform with this representation here in the Fourier transform domain. So this will be possible only if the region of convergence of the system, see here, includes z equals e to the j omega, which means the unit circle. Okay, so only in that case this is e to the j omega, can be plus or minus rotating. So now from here we can extract a lot of things. For example, we have to remember that this is usually it's a complex value, which means that we can actually separate these two analyses, the magnitude analysis, which is the length of the vector, and the angle, right? And we know that this goes in complex exponentials. When we multiply, we actually magnitude multiplies and the angle will add. Okay, so this is important to notice. And so there's a lot of other things that we have to do with. So we talked a lot about the magnitude, but the angle has some interesting properties that we need to also to understand, because it's associated with the delays and so on. And so there are some notation here. For example, what is the principal value of the angle? It's the 1/6 to this interval minus pi to pi, because when you remember that we have been used to work on this for a given, sometimes we even normalize it to 1 and so on, or this is the sampling frequency divided by 2, many ways to represent this, but usually we work with minus pi to pi. It's very convenient. Yeah, also if we are looking for the actual angle, so it's then this principal value plus minus some constant that can actually depend on can be frequency dependent, multiplied by 2 pi. But one important thing that we are looking at is the group delay. Actually there's a minus here, which is minus the derivative of the angle with respect to the frequency omega. This will tell us quite a few things about systems, and I will connect it to an example here so that you can understand these things about angles and so on. Let's say that we have this ideal delay system here defined as so this system here, we just apply a delay by nd samples to a given signal. Okay, so if you go to the table with the Fourier transform, you'll see that the Fourier transform of this is e to the minus j omega nd. Actually, if you do it here if you do it here, you see that if I apply the Fourier transform of this n by infinity to infinity delta n minus nd e to the minus j omega n. Let's say that this will exist only for n equals to nd, so the result is actually e to the minus j omega n d, as you can see here, because this delta only has one sample located at n equals nd. All right, so that's the ideal response. So if you look at some of these things that we see here, it says, oh, if you take the absolute value, I know that the absolute value of this exponential will be 1. The angle is what you see here. Okay, this is the angle that is multiplied by j, so minus omega nd. Now the group delay, which is how much we are delaying, that you can see from here, for example, nd. So how do you get this? This is actually the amount of delay that you have, samples that you have there, is the negative of the derivative of the angle with respect to the frequency. So and then when we apply the derivative here, you see this is a linear function of omega, and the result is nd. So we are in this system that we have a delay of nd samples. And this is important to have this connection, because we will be talking about now, I mean, some of the exercises involve this idea for linear systems and so on. So this is because in some cases you will have the same amount of delay in all frequencies. But what I will do before I go into details of some interesting things here, first let's take a look at this picture here, where we have the z-plane, okay, and this red circle here is where the Fourier transform exists. So here we have a system with 4 poles and 4 zeros, but they are distributed in some way that the unit circle is not affected by them. So when a pole pulls up, for example, the zero is pulling down, and they do it by the same amount, I mean the same effect at the unit circle. This pole and this zero, they have the same effect. So the frequency response is constant here in amplitude. Okay, the phase, the angle changes, but in amplitude it's constant all the way. This is what we would call an all-pass filter, that with this particular distribution of poles and zeros. Okay, let's look at this problem. This problem 5.1. Okay, this is connected to what I have just said. This is one of the problems that you have to solve. Let's see if I can retrieve the. So this problem says that in this system h of e to the j omega, this system is an ideal low-pass filter, and you have to determine where, for some choices, some choice of the input x of n and cutoff frequency omega c. So we have here the frequency domain representation of this system. If we could have this kind of output, okay, so let's see what we have here. Start sketching some things here for you. So when I analyze this output, that I'm trying to figure out whether that could be possible or not. Now this is something very interesting, that the way we do it. So we can just look at this guy here in the frequency domain. So this output, if I want to look at it in the frequency domain, then I just find its Fourier transform very quickly. I can write it should be for n minus infinity to infinity, but I know that this sequence is finite. It starts at 0, equals to 10, and e to the minus j omega n multiplied by 1. I'll put it here, but it would not be necessary. So now when we apply the formula, I hope you remember this as well, but anyway, I will write it down here. So this form that we will be using, maybe it's better I write it here. It's sum for n. We learned that this is equal to alpha to the lower limit minus alpha to the upper limit plus 1 divided by 1 minus alpha. So this is what we can apply in this simple example here. So this will be equal to the lower limit is 0, so this to the power of 0 will be 1 minus it to the power of when n is up the upper limit plus actually to the power of upper limit plus 1, which is 10 plus 1 is 11, so it's here multiplying by 11, okay, and 1 minus e to the j omega, which is in this case this is our alpha, okay, j omega n. Now it's interesting how we can simplify this. Well, let's do something very simple here, which is to see where this is located, because what I need to do in order to simplify, for example, I would like to write it as a cosine or a sine, but I need to know these basic things. Cosine of theta is equal to j omega j theta plus e to the minus j divided by 2. So this I need to know. This is an interesting way, opportunity to use. See, so whenever I have a sum of complex exponentials, where, for example, if I'm adding and they have the angle is one is negative, the other, then I will end up with 2 cosine. If I'm subtracting them, I will end up with 2j sine. Okay, so here I see that I don't actually have this, but I could if I try to shift this down, so I could write it as a sum. I have already calculated the sum, sorry. So here I will have e to the j omega 11 divided by 2n minus e minus j omega 11 divided by 2n 1 minus actually I will do the same here. I'm halving this so that I could put part of it here, but then I would factor out the other half, which is e to the minus j 11 divided by 2n, and here I will do the same, but the half that will come from here is just e to the minus j I forgot the omega here, omega divided by 2n. Okay, yeah, that's simple. And here then I would have e to the j omega j omega divided by 2 minus e to the minus j omega divided by 2. See that if we multiply, then we will end up minus plus will cancel, will be 0, then we have 1, and this will go back to what we had before. Okay, so this is an interesting way. And at the end, what we will have is so this is 11 divided by 2 minus, because the angles will subtract, it will be equal to e to the j omega 5 e to the actually this now it's because I'm subtracting, as I say here, it's a sine of omega 11 divided by 2n, and here I will have sine of omega divided by 2n. So this is then the system that we will get. You see, so this signal here, well, you can do it in a cleaner way yourself, but I see that this response here is it's kind of, so it will be, you will have some energy in all frequencies. So if we go, so it's a full band signal. If you go back to this example here, we have a low pass filter here. So the thing is it possible to have a signal that you can pass through these low pass filters to get this signal which is full band, and this low pass filter is ideal. So here you'd have 0, but this signal here, it has energy in all frequencies, you see. So in this case, then we will say that the answer is the only possibility that you could have a signal like this is, first, this band must not be restricted like this. It could be omega c must be equal to pi. So you should be here. And second, then if you have this, you extend it like that, then this actually, it's a null pass system. If it's a null pass system and you have this signal coming in, or any other signal coming in, you'll not be able to get this signal itself. You have to have this signal itself. So the only way then to get this y as output, then the input x of n must be equal to the output y of n, and the frequency must be equal to pi. Okay, I'll put it in absolute value because it's minus pi or pi. So so that's the idea. First, you analyze the signal by applying the Fourier transform to it, and you figure out that it's actually a signal that is full band. So there's nothing here telling you that it doesn't have energy in some particular frequency. So all frequencies are excited, and because this is ideal. So first, if it's like this, then you will kill all the frequencies on these bands that will modify this signal here. Okay, and if you expand to make it full all pass, then the only possibility then the input signal must be equal to the output that you see there. So that's the answer to the question. I gave it away to you here, but it's you have the job. It's your job to put it together. So now there's something else that I would like to discuss with you here, which is actually connected to problem. Make sure. So here you have explained two problems, 5.1 and also problem 5.34. Okay, when you look this video, you will be able to solve that one immediately. So this has to do with the effects. Now talking about effects of group delay and attenuation. So group delay, remember, is the amount of samples that a signal is being delayed by the system. So in this example, I have this MATLAB file on Canvas. By the way, you can also export it in the PDF format if you want to. So we have this system. This system has two parts. It has this first part here. I will have it in detail on the other side. But this is what we would characterize an all-pass system on this side here. The idea is to include more time, more delay to the input signal. But so basically the poles and zeros configuration for this system is like this. So we have a 0 on this angle because let's assume that it's real, so we have this symmetry. What we analyze for one side, it's symmetric, okay, and we have a bunch of zeros and poles in this configuration where they are actually canceling each other out the same fashion that I showed you in this transform here. So I have a pole inside, so that system could be like causal, but you have a 0 on the conjugate reciprocal. For example, if the pole is at r, some r inside the unit circle, e to the r z, no, sorry, r e to the minus j, some angle, okay, then the 0 must be at its conjugate reciprocal, means 1 divided by r e to the j. So at the same angle, but the reflected outside the unit circle in this case, because here we were imagine that r is less than 1. Okay, right. So this is the system. Let's look at this. So if I look from here, what should I expect from this? So I expect this pole here is giving some gain. As you see, what the pole does is it gives some gain. Okay, modifying this, it can affect the unit circle. In this case, it didn't, because we have this all pass configuration of the 0 canceling the effect of the pole, and here then we have a bunch of them canceling in this configuration 0 pole, so that you can have all pass on this part here. But we have this pole here at this angle, which will give a huge gain. These zeros that will probably zero any signal that is in that angle. So repeating again, if we have any signal coming at this frequency, they will be allowed to pass. And here you'd have attenuation. What I say from that one is the same that I could say for this one, because it's symmetric, and here as well. And here, if we have any signal at this frequency, it will be cancelled. Okay, so I will just make a very quick sketch of what I could expect from a system like this. So if I go from here, so in between this, see, 0 here, I have this effect of this, but I don't have much gain, but I don't have much attenuation either. But when I approximate, so the angle is increasing like this. Okay, when I get close to this pole, I will have some, but it doesn't go like this one. Okay, because we are not showing what is happening exactly at that point, but rather we are showing what is happening on the unit circle. So when you have a pole close, it can modify it, can go up like this, but not by much, all depending on how close to the unit circle the pole is. So here, this pole here would get a gain, and then at this angle, which is very close to pi, it's more or less 0.8, so pi, at this angle it would go to 0. You see, we'd get something like this, and then you'd reflect to this other side here. But let's look at the actual picture. Is this one? So this is the frequency response, which is a reflection of what we have discussed about the zero pole location. Okay, now the group delay, which is something very important, it's the derivative. So when you have a steep, so here have a huge delay here because of this in the angle, because this is the derivative, which is the slope of this curve. So sometimes see the group delay is almost zero, where the slope is not very much. Yeah, so the slope is close to zero. Okay, because one is derivative of each other. So this is the group delay. Then what is the we have in this example here, which is similar to problem 534, is the following. We have now three signals, three pulses, narrow band. That means actually it's one frequency here, one frequency here, one frequency here. We don't have too many frequencies. They are just modulated. That means the shape changed, but it's one frequency. It could be one cosine, but the shape was changed. So here are the two frequencies. This plot is like we have two sides, but remember, actually is 1, 2, 3 frequencies. This is the negative part, but it represents. We can analyze just this side if we want to. So we have a frequency at 0.1, 0.2 pi, 0.4 pi, and the other one at 0.8 pi. Okay, so the highest frequency is this one here. Higher frequency, lower frequency is the medium frequency. Highest, lower, medium. Okay, now if we compare with the response of the filter, what do we have? That at this frequency, which is the medium, we have some amplification. Okay, you see, we have amplification here. This is linear scale, so almost double, a little bit more than double at this frequency. So the medium frequency will be amplified, but it will be allowed to pass. All right, that's one thing. Now at this higher frequency, we have a zero, which is at this 0.8, sorry, that you can see here in the pole, so in the zero pole plot. So we have a zero there. That means that any signal that comes at that frequency will disappear. The zero is on the unit circle. If it was inside, it's not. It was not. It would not be the same. Okay. So we have a huge amplification here for this frequency here, which is the medium. Minor mild amplification, almost equal to 1 for the lowest frequency, and the highest frequency, it's been cut. Okay, so when this is then the input, how they came in this order, and now when they came out, as you can see, the higher frequency disappeared. Okay, higher frequency is not there. We have then only the medium and the lower frequency. Well, that's one thing. So first analyze the the frequency response of the system to see who will be allowed to pass and who will not be allowed to pass. Here, then the conclusion was the higher frequency disappeared because the system had a zero. At that frequency. See, it goes to zero here. So this on the output, the higher frequency disappeared. But then we have the two frequencies, the lowest and the medium. But we can see that compared to the input, they are swapped. So that means that they receive different amount of delays. That has to do with the group delay, which is part of that exercise too. So in that problem, I need to call your attention to this, is the fact that when you look at these plots, you see they look similar in size, but actually you look at the scale, you see 1, this is more or less up till 2. This is to reflect the amplification that you had in this frequency. But here the maximum was 1, okay? So pay attention to this, where you have amplification or not. So as we said, at this frequency, the medium, we had amplification with a little over some amplification almost double here, maybe a little bit higher, okay? And this frequency 0.4 here, which is the frequency of the medium signal. So it was amplified. Look at the scales again, calling attention to this, where 1 is and where it is here. So pay attention to that. First, analyze the magnitude response, which is amplification, attenuation, or in this case we had also a 0, which means a frequency disappeared because it was on that frequency was in the part of the system where you had actually lower gain in some region, but exactly at 0.8 you had a 0, so it disappeared, okay? Yeah. And so the second thing is why are they swapped? That has to do with the group delay. So now we analyze the group delay. It says that the lowest frequency, which was 0.2, remember we had 0.2, I will mark them here, these were the frequencies that we had. This one here disappeared, so it's out, okay? But the other two, the one that was at 0.2 was delayed by 150 samples, all right? And this one here at 0.4 was delayed by very little, almost 0, okay? So let's go back to the picture. So these two frequencies, this one was at the 150, it was delayed by a little, so a little bit over 150. And this one here was delayed by, again, let's go back to see the group delay here, by 150 samples, right? So let's look at it. This frequency here was centered around maybe 80, and it went to, let me see, is that correct? 150 samples, so over 200, okay? It was almost at 100 plus 150, almost to 250, so that's correct, okay? So here we pay attention to two things. First is analyze the gain, who is being amplified, who is being maybe kept more or less the same, and who is being cut out by zeros, for example, amplified by poles. And then we also analyzed who is being delayed the most or the least. That has to do with group delay. So in this exercise that I'm talking about, 534, you have to analyze exactly this, but I'd like you to provide some explanation to what you see. See if I can take that example here. basically that's all. If I can find it. So here it is. Let's see. So here we have, give you some hints about this problem here as well. Here I have the system. These are the three signals that you have, the frequency spectrum. Here you have them only one side, from 0 to 1, okay? And so we see that this system also has a 0 at this higher frequency here. So expect that from these input signals that I see here, the higher frequency will not be at the output, so this one will disappear. All right, and we will be keeping the two, the medium and lower frequency. But then, so the medium frequency, it was given in the text. You have to go and read what the frequencies are here. 0.5, which will disappear. 0.3, which has minor attenuation, minor amplification, and point something, maybe 12 or something like that, which has a little bit more amplification. So now your job will be to look at these two things that I told you about. Amplitude response, which is which frequency will disappear, and then delay. Okay, so for amplitude response, you can see, I will not tell much because I think with what I said you can figure this out. One thing for sure, we know that the higher frequency will disappear. Then it cannot be this one, because I see the higher frequency here. It cannot be the first one, then it cannot be the third one. It must be one of these. But then you will figure out by checking who is getting the highest delay, the greater delay, which you can see from the group delay. See, this is the delay that the lower frequency will receive, and this is the delay that the medium frequency will receive. I think now you're in the position to give the right answer to this. Okay, guys, let's finish here. It's almost 40 minutes, too long. I didn't mean to make it so long like this, but good luck with these two exercises. I will post, I think we need one more video just to post a few other details about the other exercises. Thank you very much. Bye bye.